Good morning. My name is Oluwakai de Bamaduro. I'm a graduate student here at Norfolk State University, and I'm here today actually to describe a wonderful piece of equipment. It's a physical vapor deposition technique, and it's called Magnetron Sputtering. To my right is the control panel to operate this fully automated system. Adjacent to my right is the load dock area where we load our samples. And adjacent to that component is the deposition chamber. And inside the deposition chamber, you see that you have several target guns, and they have lids on top of them. And again, this is how the target will look. This is target number 3, as I'm pointing to, is ITO, indium tin oxide. And say, for instance, we want to deposit ITO onto a substrate. The substrate will be located directly above the target guns and is being mounted onto a sample holder. Of course, the door will be closed. It will be under vacuum. And we insert a gas, in this case argon gas. It's an inert gas. And then the argon gas has positive ions, and we have an RF power at the particular gun that we're interested in, and it's going to cause an attraction. And then that attraction is actually going to etch some species of the ITO in form of a plasma onto the substrate, which is located again above the target. Now you can vary the power, you can vary the pressure, and you can also vary the temperature as well. All those different conditions determines the outcome of your thin film. The substrate could be glass, it could be quartz, it could be silicon, of that nature. Now this is how actually the deposition would take place. As you can see, this particular component came from a 0-0 axis, or we'll call it a home reference, and we extracted this membrane all the way down to its full extent. And then you'll have a mechanical arm coming from the left side of this compartment, whereby it would transfer the substrate into this location here. Once that is done and all the operating conditions are met, we'll have this particular shutter pop open, and the plasma will take place, whereby it's going to etch the material of that target onto the substrate that's been mounted vertically above these guns. This is how magnetron sputtering, or any sputtering device, typically works. Argon gas comes into the system, and below you have your targets, and that is labeled as a cathode. And on top here, where the substrate is being mounted, is your anode. So at the target, it's going to be a negative power, and the argon gas coming in positive ions. The attraction could be mild, or the attraction could be hard, again, depending on how much power, how much pressure is being, this particular deposition is going to take place. And then once this attraction happens, this material is being etched off or removed from the target, and that causes a plasma. And that plasma is being deposited onto the substrate, which is located directly above the target. This is a microscope slide. We're going to use about 3 screws to fasten this piece down so it doesn't move under deposition. This particular piece of machine can be used for manufacturing purposes on a large scale, whereby you can deposit a number of thin films at one time, say within 15 to 20 minutes. Also, this particular sample holder can hold a minimum of 4 to a maximum of about 6 slides, and that is good for not only research purposes but also for manufacturing purposes on a very large scale. We've mounted our sample onto the substrate. We'll do a check, make sure it's fully fastened. So we'll shake it, make sure it doesn't move, still fastened. Now we'll open up the load lock chamber. It's been inserted into the chamber, and now the door is closed. And this compartment will also be under vacuum. And when the vacuum of this chamber and the adjacent chamber are the same, then the sample will be transferred to the deposition chamber. Now, I will take you through a series of steps on how this mechanism actually works. We come back to my left. This is the control panel. This is the automated control system that controls the whole instrument. Again, this is a vacuum-based technique. We have several pumps here within this mechanism, and we first start off with the roughing pump. And then we have a PC turbo backing valve, and then we have a turbo pump. All this is attributed to the deposition chamber. Now, to my left is the load lock. This is the area where the sample is being loaded, and it also has its set of pumps, which are 2. Above it, this area right here gives us information of how the load lock compartment is operating in terms of its pressure, and then to the right is a bigger screen which gives us the conditions of the actual deposition chamber, and it has more information such as temperature and pressure. Now, in an event where we want to make a deposition, we actually have to vent the load lock, which is this button, the last button on this column to my right. And we vent this particular compartment to atmospheric conditions, whereby we can open up the compartment, place our sample in, and then we close it again. We'll evacuate it and bring it under a certain vacuum. Then the next step is to transfer that sample into the deposition chamber. And we do that by the third button from the bottom, which says Start Sample Transfer Load. So there's a mechanical arm that would actually transport our sample from the load lock to the deposition chamber. That's actually done by a recipe. Now this machine operates by what we know as a recipe, and a recipe is just a number of steps or a number of instructions whereby you accomplish your deposition. And mind you, you can set up any recipe for any kind of conditions you want to do, and it ranges from temperature, pressure, and time. In this case, we want to deposit molybdenum on the substrate known as soda lime glass. Now we have a series of steps, and it's going to transfer the sample from the load lock to the deposition chamber. And in between that, it goes through a series of steps, more of checks and balances, make sure everything is calculated properly. In a real life situation, you're not actually going to see all these steps, but you'll have a window that actually highlight the step as which is being executed. And what's so beautiful about this system is it checks for all conditions, and if the condition is not met for that particular step, it will abort that particular procedure. So that allows us to go back to see why or what happened as to why that step was not executed. So once the script has been executed, or once the recipe has been executed, the sample has now been moved from the deposition chamber back into the load lock. And then once this has been devacuumed or actually brought up to atmospheric conditions, we can now open up the load lock chamber, and take out our sample. And this is our sample after the run has been executed. Initially, when we want to make a deposition, we clean this glass slide, which is just a bare glass. And after the deposition is done, this is what we have. And this one, in this case, is AZO, which is known as aluminum doped zinc oxide. It's a transparent conducting oxide. And what that means is that it's just highly transparent, but however, is a semiconductor. And now we can vary the thickness, or we can vary any of the properties based on the deposition condition. This is another deposition that was made. This is molybdenum deposited on soda lime glass. And this molybdenum is known as it's used for a back contact for solar cell applications.